Okay, hello everybody. Thanks first of all to Adrian to inviting me to present at this symposium. It's great to see the evolution of the open media movement over the last few years. Just to fill in some blanks here, I used to be a professor at Trinity College Dublin. I spent 6 years working with Google YouTube. Now I'm back with Trinity College in the signal processing for media applications group. My research assistant, Devinder Singh, is responsible for a lot of the experimental work that you'll see here today. And I am going to be speaking about motion-based video frame interpolation. So just to give you an idea what I'm talking about here, so the top panel in this panel of 4 shows a 30 frames per second sequence, and the bottom 3 panels show 60 frames per second by upsampling that 30 frames per second by a factor of 2. Those 3 panels show different algorithms that I'll be talking about during the rest of this talk, but basically the message here is that frame interpolation has been around for quite a very long time. So as an effect, interpolation has been used for slow motion, for frame rate conversion, and so on. So on the left here, I have just drawn 3 different popular effects that are used in the post-production industry. So this is slow motion from 25 to 75 FPS played back at 25. The circles are the locations of the existing frames, and the diamonds are locations of interpolated frames. And this is a sort of classic frame rate conversion problem, 25 to 30 FPS. And here is something popularized since about 1999 with the Matrix series of films. This is deceleration. Everybody could spot that as deceleration, right? We're starting at 25 FPS and we're going to 50 FPS slow motion by a factor of 2, and gives us an emphasis of force. In video codecs, frame interpolation is arguably the heart of any video codec, right? So inside a hybrid video codec is this motion compensated predictor interpolator, and the better that is, the better your performance at video compression. So what I'm going to do first of all is to review traditional work in motion-based frame interpolation, talk about the recently emerging work in convolutional neural nets for frame interpolation, present sort of traditional view, a Bayesian approach to motion interpolation and the corresponding algorithms, but sort of highlight these things, right? So we're going to compare all these technologies using a pretty large data set, and in particular, compare with state-of-the-art software available in the motion picture effects industry. And it's probably quite it's quite good timing to be doing this talk this year. This is the 20th anniversary of the Matrix, when a lot of the ideas of optic flow in special effects started around 1999, 2000, and so on. I just want to point out that with the rise of convolutional neural nets, I'm starting to see more of a crossover between computer vision and signal processing, especially in this area of frame interpolation. So, right. In the signal processing community, people sort of know this for a long time, that if you assume a simple rubber sheet model for video, so every frame you could build by rearranging pixels in the other frames, then once you know motion, you're kind of done. So here are 2 frames in a sequence, and I represent these things as little 1D sticks, and this is an object moving simply through that 2-frame sequence. My frames exist at time t and t plus 1. I want to interpolate a new frame at time t plus delta, and we could see at this site here, if I knew what the forward and backward motion was, I could reconstruct this pixel color by taking a weighted combination of those 2 pixels like this, right? So I just need to know those 2 displacements and those 2 weights, and we're good to go. Of course, some cases I can't do that, so I need to know what areas are occluded and what areas are uncovered. Now, like I say, in the signal processing community, people know this for a long time. So since about 1996, that's probably the first example of somebody explicitly, so Castagno and Havisto, explicitly enforcing this thing called symmetric motion estimation or bilateral motion estimation or bidirectional motion estimation. It's all the same. What you do is you simply perform your motion estimation with reference to this missing frame, and make sure your forward vectors and backward vectors are mirror images of each other, and you could build that missing frame. In 2007, that was sort of finessed a bit with overlap block motion compensation to give pretty good results, and that's actually used in FFmpeg today. But of course, the most recent exciting development is convolutional neural networks, and since about 2018, some very interesting bits of work have emerged to try and do this effect with neural nets. And we could classify the two bodies of work with these two representative papers. This is something presented by a team at NVIDIA and CVPR 2018. In fact, digging beneath the hood, you realize actually they're just doing motion interpolation followed by picture reconstruction. So they're estimating optic flow with a convolutional neural net, and then generating the missing frame, a first guess, using traditional motion compensation ideas, and then doing a refinement with another convolutional neural net. And in fact, using this very same equation to estimate what those sort of visibility maps, they call them, should be using that neural net. Over here, Nicklaus et al. Well, since 2017, they have about 3 papers, have built on some of the ideas that are, again, sort of known in the signal processing community. And if you look at what they're doing here, they're building that missing frame by a weighted average of 2 frames, but that weighted average is based on 2 filters applied to the forward frame and the backward frame. And those of you who remember your signal processing literature from way back in 1975 might remember something called spatio-temporal autoregressive models. And it's very, very similar to that, except with the beauty that these filters can change from pixel to pixel, and that is estimated with the convolutional neural network. Now, that's all I'm really going to say about neural networks, because when I look at that literature, I tend to feel like this guy here, right? I think a lot of people in that same boat. So I'm not going to say too much more about those algorithms, right? I'm going to turn to what these days people might call old-fashioned Bayesian formulations for these ideas, and I tend to start a lot of my talks like this, right? Start really high up and then sort of skip all the middle bits and go straight to the end. So what we're trying to do is to build a missing frame and the missing motion given our observed information. So observed motion and observed frames and so on. So in a classical Bayesian fashion, I'll use the English translation here. I'm factorizing my posterior with these 2 factors. So one factor is this missing motion given observed motion, and the other factor is the missing picture given the missing motion. And that's the way most people think about this. Build the motion first, and then build the picture. But you could see that, you know, you're actually making an assumption here that you could factorize your PDFs like that. But for those of you familiar with this sort of way of thinking, the next step is to define our likelihoods and priors, and then we're more or less done, right? Now, a version of this algorithm has appeared as the YouTube slow motion algorithm in the upload enhancements pane for a few years from 2013 to 2018. It was pulled down for various reasons, restructuring editors and so on. And I've never really spoken about this algorithm in this context before, because in my crazy mind, a lot of these things sort of come from motion picture restoration work, where we were trying to rebuild small patches of missing data in video. And you could see this algorithm as just a sort of natural extension of a lot of those ideas. So, like I said, I'm going to skip all the middle bits, and whatever you do is going to boil down to some kind of energy minimization problem. And the algorithm you'll have is 2 steps, fixed motion and then fixed picture. And in the interpolate motion part, you're going to, first of all, estimate motion between the existing frames. If you like, it could come from any motion estimator, even from a compressed file. And then you're going to be iterating over blocks or pixels. And in each one of those sites, you'll measure some motion energy, some picture energy, some occlusion energy, and pick the motion which minimizes that energy. And then you're going to interpolate the picture using occlusion. And as any good engineer would do, right at the end, you have a little post-process trick which will fix all the things that you got wrong in the first parts of your workflow. So in this algorithm, we actually use 4 frames. And the key thing is to encourage motion smoothness over those 4 frames. So given these 4 frames, problem is to interpolate this missing frame. And you have motion forward here, backward here, and forward and backward between those frames. A lot of what I'm about to say has echoes of what Ken Rose was saying yesterday, right? Use motion that exists to try and build motion that doesn't. So to define motion priors, you could kind of see where we're going here. If you assume linear motion, these trajectories should all be smooth through those 4 frames. So if I look at this first energy, for instance, what I'm doing here is making this interpolated motion be similar to this motion existing between the forward 2 frames, scaled by the right temporal displacement or sort of temporal interval. And then this energy term here is doing is just encoding the mirror constraint that the forward motion should be equal to the backward motion. So I could take my existing backward motion, scale it, and use that as a constraint for my forward interpolated vector here. And then this guy here is the same thing in the backward direction. And I could do more in this backward direction here, comparing this vector with this one. So that gives me 4 energies that I want my interpolated vector field to comply with. It turns out that it's better or more powerful to attach occlusion to motion than it is to attach to the picture information, right? And in fact, what we have set up here is 2 energies that kind of fight each other, but come up with some compromise. So if I take a look at these, so these you could, depending on how you look at them, you call them likelihoods or priors. But if I look at this energy term here, what we are saying here is that, okay, this is occlusion, but let's say it's occlusion in the forward direction. If occlusion occurs in the forward direction, then we expect motion to be smooth in the forward direction only, because in the backward direction, we're not going to get any match. So I sort of turn off the backward smoothness constraint with these penalties, right? And then I have similar sort of thing in the backward direction. And then when when I know there's no occlusion, then all these vectors should be equal, right? So, or not equal, but agree. So I have an energy here, which adds up the sort of differential vectors in time. The associated image likelihood is a bit different and it's simpler. So all we're saying here is that this thing is encouraging pixels here and here to look the same. So I would prefer in this, for instance, here, my backward vector and forward vector to associate these 2 pixels together instead of associating these 2 pixels together, because these 2 look the same and these 2 look different. Up here, I would prefer a vector which starts here and ends up here. So a funny way, my image constraint sort of encouraging acceleration, but my motion constraint is not encouraging acceleration. And that turns out to be a good thing to encourage. Now, so at this point, I should say we've been developing these ideas over many years, right? Started work way back in 2000 or something. And what we noticed quite early on, well, especially Now you could see that at this point, you have a lot of available optimization schemes to do a good job here. So you could use belief propagation, you could use graph cuts, and so on. But it turns out, because motion is so smooth over time, you could do a really fast, good initial estimate from which a few iterations will get you where you want to be really fast. So here is an idea that we use quite a lot. So for instance, we have existing motion between this frame and this frame. So it makes sense if I just walk along this vector trajectory, see where this vector hits here, then this forward, I could take my vector and divide by 2, and this becomes my guess for that forward motion. And I could do the same thing in the backward direction and get a hit in that direction. I could also do some really interesting things here and notice that if I have loads of hits in one direction and none in the backward direction, it's probably occlusion. So once I get to that point, I could now start in that space and then do some local iterations. We start off with gradient-based motion estimation over blocks. We generate motion candidates. We extend those motion candidates with occlusion states. And we just test all the candidates and pick the best, right? And converge quite quickly. So I just want to go through a few results here. There's quite a lot of information on this slide, and I'll walk you through it. First of all, we compare, 7 different motion interpolation techniques here, right? And these two are called Kronos and Twixtor from 2 companies, the Foundry and Revision Effects. And both of those teams won Academy Awards back in 2007. So I was working with these guys at the time, and they were working on some of the Matrix movies. And Revision Effects, those guys are still going, and they're here in San Francisco, Pete Litvinovich and Pierre Yasmin. And we use Adobe data set that a lot of people have been using, 240 FPS. I downsample those things to give me 30, 60, and 120 FPS, and then upsample, so I have some ground truth that I can measure PSNRs with. There are about 14,000 frames here. And just by the way, Kronos is like a commercial implementation of this thing, and this is the algorithm that I just presented to you. So I was quite glad that after all these years, the motion-based interpolation using simple ideas still comes out on top, right? And the convolutional neural nets not quite there. But then a lot of people are beginning to realize that averages is not really telling you the whole picture, right? So in fact, if you look at the confidence interval or tests of significance for your means, you'll find that all these 4 methods are practically the same, right? But they're very different and better than the other neural network approach and FFmpeg and so on. Another interesting thing is this. Well, look here, you can see going from 30 to 60, 60 to 120, and 120 to 240, the PSNRs improve quite a lot, but they improve more from 30 to 60 than they improve from 60 to 120. So it's easier to interpolate frames from 120 to 240 than they are from 30 to 60. But that makes sense because 30 FPS, you have bigger displacements than at 120 FPS. What's interesting though is that 60 FPS is like a breakpoint. So beyond that, it's almost as if beyond 60 FPS, we should be able to interpolate frames perfectly, even if we recorded them with a really good camera. Here are some distributions showing that information in a different way. In particular, outliers are important. And between here and here, you can see not much change in that in that slope, but over here there's a fair amount of change. I just highlight a couple of things. Phase-based technique is the worst. Phase-based should work a lot better than this. I think there's something wrong here in the motion estimation. And this is the median value, and you can see the big jump going from 30 to 60, and then not much going from 60 to 120 to 240. Okay. Another thing we've been doing to try and capture how good things perform is to do this sort of ranking. So for every sequence, we rank, which one is best, which one is next, and so on, and build these little bar charts. So red bars mean this is the number of times that you were the best, and number of times you're the second, third, fourth, fifth, and sixth, and so on. And for 30 to 60 FPS, okay, we could see that Twixtor is the best. It turns out over the whole range, Kronos is the best. It comes first the most number of times. The algorithm I'm talking about in this particular form comes out the third, and so on. Here are some visual results, and you could just see here that the neural network technique is struggling with the with motion at the boundaries. So this is 30 FPS, and these are 60 FPS versions, and these two versions look almost identical. I will just move on quickly to this and show you a really interesting thing, that no matter what you do, everybody struggles with complicated motion. So it's in fact, with small, thin features, you find all the techniques kind of fall apart. You can't tell the difference between foreground or background. And then post-production, nobody would ever retime sequences like this. They would separate the layers using rotoscoping, retime them separately, and then put them back together. So there's some interesting work left to be done here. Finally, this is one example that the DeepNet actually does perform better than Kronos, but it turns out it's still hard to see. You have to look at the bicycle wheel on the back of that car to see the difference. But I wouldn't spend too much time talking about that. Okay, so just in summary then, 60 FPS is a sort of breakpoint for temporal aliasing for this problem. CNN methods seem to be about the same or a little worse than Markov field motion interpolation. All the successful methods use motion explicitly, and if your motion handling fails, you're out. It seems as if a good way to the future is hybrid Markov random fields and CNN methods. And just as a final thing here, this sequence is about 20 years old. It was one of the first sequences we experimented with in those early days in 2001, trying to develop sort of view interpolation techniques for those matrix episodes using these ideas. On the left is 10 views, on the right is 20 views using Bayesian interpolation. And if you look carefully, you could see the thing a little bit struggling with occlusion and uncovering. And that's what the future is, to try and fix those things better now. Okay, thanks very much.
I can start.
Go ahead, and then we'll go to the back.
Is there a microphone? Here.
Thanks, Anil. Quick comment. So in order for this to be useful, let me say in the video compression setup, the question is, what's the sensitivity in case of your frames to be interpolated not being perfect? So in the presence of compression, typical compression artifacts, how would they affect?
It's a good question. In fact, we're looking at that now, actually trying to rebuild frames based on motion vectors from the bit stream. Right? And you're right. I can't comment a lot on experience right now because we only just starting to experiment with these things. But with the right motion smoothness constraints, I think you could build pretty convincing in-betweens.
Back.
Oh, so first of all, thank you for your presentation. And may I ask, have you tested all these methods on dynamic texture content?
Oh, yeah.
Like water or smoke?
Yeah, and it works really good with water and smoke, especially visually, because nobody knows what slowed down water and smoke looks like.
Thank you.
Yeah, in fact, those are the best examples, water and smoke.
Yeah, so you mentioned like accuracy of the motion is very important for this type of interpolation or upsampling. So based on your experience, like how fine you want the motion to be like per pixel motion or per block motion, a certain, what's the threshold you have been seeing?
So a good question. It depends on the resolution of the original material. And in fact, for a lot of these things going down to, you could stop at 2x2, 2x2 block, for instance, and quarter-pel motion estimation accuracy. In fact, I didn't say that, but we actually pruned the candidates with a really crude vector quantizer to throw away vectors that look the same within plus or minus a quarter pixel. And you find that you reduce the number of your candidates by more than half really quick. So you don't have a lot of change from iteration to iteration. You end up very rapidly getting just to those motion edges and finding you're spending a lot of time at the motion edges getting things right.
Okay, sounds like we should have the 2x2 blocks in EV2.
Maybe that might be too much for compression.
So first, a comment on Ioanni's question. In MPEG codecs, already they're using frame rate conversion as part of the codec, but it's a mode. So the encoder makes the decision, and if it works, you're like, because you have the original reference, you can actually use FRC techniques. It's just you're pushing essentially more complexity on the decoder because it has to do this kind of a decision. I actually like the comment that you said at the end, moving from that point about creating combined methods between, let's say, conventional motion compensated techniques and neural networks. And to me, it seems to make sense that, we do create maybe a frame using, conventional motion compensated techniques, and then use post-processing techniques like other people have shown to maybe go and correct essentially all the artifacts that we have, let's say, created through the conventional techniques. And I don't know if anybody is investigating, but I think that's definitely something worth looking into.
You're definitely right. That's the way to go. When you look at these techniques, 90% of the surface area of the picture is solved with the simplest technique. And you spend all the time at motion discontinuities. So anything more you could do there, that's where the energy should be concentrated.
Okay, great. Neil, thank you
All right,
very
thanks.
much.